Okay, let's get started with our 10 a.m. press conference. This is about small climate changes and big ecological impacts. Our speakers in this order are Daniel Mann. He's an assistant professor at the School of Natural Resources and Agricultural Sciences at the University of Alaska Fairbanks. Peter Beck, he's a research associate 2 at the Woods Hole Research Center in Falmouth, Massachusetts. And our third speaker is Andrea Lloyd. She's a professor at the Department of Biology at Middlebury College in Middlebury, Vermont.
Good morning, and thanks for coming. So, actually, we like the title of the press conference better than we like our session title. But what we're going to talk about is 2 examples of ecological regime shifts. These are radical changes between contrasting states. So my analogy here is you're headed down a river in a nice canoe, it's a sunny afternoon, and suddenly you flip over. So in ecological terms, it would look something like this. Some ecological regime shifts from being upright in your canoe to upside down looking at fish are catastrophic in nature. So they have abrupt thresholds, no intermediate states, and they experience hysteresis, which basically means you don't get back to where you started the same route. Is there a pointer? Here it is. So we could have slow forcing. So let's say environment's changing, like climate is changing slightly, and you change in response very slowly until you reach a threshold. Then you go over what's called the fold in the catastrophe fold, over a threshold, a forward shift down to a totally different state of being, from which to get back to where you started, you have to reverse environmental conditions quite a long way. So why this topic is important in general is, as you all know, we're in a time of rapid environmental change, and basically we want to know what kind of canoe we're riding in, because if you know anything about canoes, these different hull designs have different initial and secondary stability. So in other words, some of them have a much more sudden threshold to flipping over. So that's kind of the rationale for interest in this topic. So today we're going to talk about 2 possible examples of catastrophic regime shifts which have occurred in Alaska. Now, as most of you know, the Arctic in Alaska specifically experiences early and rapid climate change. So in some ways it's the canary in the coal mine for global changes. So I'm going to talk about a possible catastrophic regime shift which occurred at the end of the last ice age about 14,000 years ago. And then Peter and Andy are going to talk about a possible ecological regime shift which is threatening today in the boreal forest. So we're going to start out up here in northern Alaska in the tundra area north of the Brooks Range, and then they'll talk about what's going on in the boreal forest in the interior of the state. So here's the title of my end of ice age possible regime shift. These are my co-authors. Most of these people are still up in Fairbanks right now freezing their asses off. So the mammoth steppe during some parts of the last 100,000 years stretched from, if you could ride a mammoth, you could have ridden a mammoth from southern Spain all the way over to the Yukon, and if you could have gotten across the Laurentide ice sheet all the way into Quebec. So this was a very large biome that's totally absent today, so an extinct biome. And the question has always been, what happened to it? So here's some of the denizens of the mammoth steppe. Our key species, the namesake is the woolly mammoth. There was a kind of a super predator scavenger, the short-faced bear, and then the Beringian lion. The species in red are globally extinct today. The species in yellow are locally extinct in Arctic Alaska, which means they survive somewhere else in the world. And the 2 white species, muskox and caribou, are megafauna, which were there during the Ice Age and continued there during the Holocene. So they survived the big change. So we've known for years that there was a major change in climate at the end of the last Ice Age, but it's always remained a mystery what actually drove the sudden jump between a mammoth steppe, which might have looked like this, to a moist acidic tundra, which is what we see today in northern Alaska. This is actually a picture from Yakutia. So we have warm, well-drained soils with a lot of grass. where if you go to the Arctic foothills in Arctic Alaska today, and let's say it was July and you're barefoot, your feet would be cold and wet, the soils are cold and wet, and you'd be swarming with mosquitoes. So it's quite a large jump. So our data consists of a large number of Pleistocene bones that we collect out of permafrost along river banks. So it gives us the most detailed chronology yet from Arctic Alaska. So from within a region, bone collection of shared taphonomy. So what's shown here is that's 0, so this is the present, that's 50,000 years ago. And here's all species of megafauna plotted. The dashed line shows the sudden disappearance of mammoth, horse, and bison. So these are all from Arctic Alaska, and we have this sudden ending of these, this faunal regime. So our hypothesis is simply death by peat. And so what we're suggesting is that we had the development of a regional peat cover that triggered a catastrophic biome shift. If you go out on the North Slope today in the Arctic foothills, here's a shovel for scale. This is the typical scene. So we have sedges in hummocks, mosses, and dwarf shrubs. And then we have a peat layer, 10 to 20 centimeters thick, an active layer up to 30 centimeters thick, overlying permafrost. So again, it's wet, cold, and acidic. Now keep in mind the Ice Age had a very different tempo of climate change than the last 10,000 years. So we're looking at, here's the Holocene. So human agriculture arose in the Holocene, and our civilizations all date from this time of steady, warm climate. But look what was going on in the Ice Age. We had, here's 10,000 years ago, 20,000, 40,000. We had these sharp 1,400-year-long spikes in climate, where climate warmed rapidly for 700 years and then cooled rapidly for 700 years. So 1,400 years long. So these are called Dansgaard-Oskar events, and we start here with number 1, 2, 3, out, etc. And you can see the difference. DO number 1 was more like 2,200 years long than 1,400 years. So it was longer than the previous ones. So to put it briefly, and I hope you can come to our session tomorrow morning. To put it briefly, what we think happened was that as we went into DO number 1, the climate stayed warm and wet enough for polutification to occur. Polutification is a fancy word for the bogging of a landscape, so the spread of peat over an entire landscape. And so let's start out at 16,000 years ago. So we're beginning into Dansgaard-Oskar event number 1. We go above the 7-degree centigrade isotherm. We get peat formation. The animals love it. So this is a small group of mammoth. Now we have a whole herd of mammoth. Okay? So for a while, there are greener pastures, more mammoth, more megafauna. Then we go past the 500 to 700 year limit, which we've determined from modern studies is about the time it takes for polutification to spread over large extents of the landscape. As soon as we go over that threshold, we're falling over the fold of that catastrophe diagram I showed you early on. And now suddenly we have widespread polutification, so there's peatland everywhere, grazing deteriorates, and then the younger dryas cold interval, which followed this Dansgaard-Oskar event number 1, is not long enough to kill off the peat, basically. So we flip into this new regime state where peat dominates the landscape, and we've gone into a new biome, and the megafauna disappears locally, at least from Alaska. So that's the possible old example from the end of the Ice Age of a regime shift in Alaska. And now Peter Beck's going to tell us about another one which may be looming now south of the Brooks Range. So I was talking about the area up here. He's going to talk about down here in the boreal forest of interior Alaska. Thank you.
Good morning, everybody. I'm with the Woodsoil Research Center. What I'll show is a group effort of the group led by Scott Getz at the Woodsoil Research Center. And a lot of it relies heavily on work. Scott started with Andrew Bunn, who's in the back of the room. My main message is that at high latitudes, especially in interior Alaska, multiple lines of evidence are together showing this, to what extent ecosystems, the forest ecosystem in particular, is now responding to climate change. I'll give an update of the analysis of the remote sensing record, but we're now able to bring it together with tree ring data as well, and together they form a very cohesive picture of forest responses to recent climate change. At the same time, we're seeing changes in the disturbance regime, which in high latitudes is primarily forest and insect disturbance. And as with the warming, those are expected to increase and intensify in the future. And the confluence of those two drivers and the responses we're already seeing strongly or opens possibilities for regime shifts acting out at large spatial scales and potentially really being biome dominant. And that poses particular challenges to our modeling efforts, which now focus on feedbacks from the biosphere to the atmosphere. But because regime shifts are so hard to predict, they challenge our idea of how we model these systems. So this is the analysis of NDVI, so greenest data from the NOAA AVHRR satellite record. So this covers the period 1982 to 2008 and gives us a proxy of vegetation productivity. So this is work started by Andrew Bunn and Scott Getz, and this is basically an update as the satellite record gets longer. And the major message here is that we see this contrast between Arctic tundra, so north of tree line areas are predominantly greening, so apparently increasing productivity, which goes along with stories of shrub expansion amongst others. But then in boreal forest, particularly in North America, we're seeing browning trends, so decreasing productivity. In the center here runs an animation of what the maps look like as we get more and more satellite data. So it starts off with a 20-year record until 2002, and then now we're at 2008. And what I want you to look at in particular is, again, North American boreal forest, where you see the browning expand, which basically means that our statistical support for a widespread decrease in productivity is getting stronger. The graphs on the left show for the boreal forest the area where we have statistical confidence that there's a long-term decrease in productivity, and you see that increase as the satellite record gets longer. The graph here on the top shows the same for the tundra, where we're getting increased support for widespread greening trends. What we recently published is a comparison of those greening and browning trends, which are here shown in the background map for Alaska. So here again is north of the Brooks Range, the North Slope tundra, and then here interior Alaska. And we compared it with the tree ring record over that same period from black spruce and white spruce, which together dominate forests in interior Alaska. The dots are sites where we have tree ring collections. The triangles are black spruce, the circles are white spruce, and they're colored based on the trend we observe in the tree ring widths over the same period as the satellite data, so since 1982. And what we show in this paper is how those two records now line up very well in terms of how strong the trend is in productivity, as well as the spatial trend, the spatial pattern. So in interior Alaska, which is much drier, we see more and more decreasing productivity as you go west towards a colder, more moist climate. We're seeing increasing productivity. When we discussed this, it raised the obvious question: at what point will that, what we believe to be warming and drought-induced decreases in productivity, start translating in increased mortality? Because at some point, the trees won't be able to take it anymore. So the idea is that it's basically drought-induced. It's even though we don't think of boreal forest as generally drought-limited, the hypothesis is that it's warm, dry air masses limiting photosynthetic activity. So this is a paper that very recently came out in Nature Climate Change, which I wasn't involved with at all. But what they showed is from permanent plots at the southern extent of the boreal forest, so this is southern Canada, increases in mortality across dominant tree species. So the red circles show areas of increased mortality, and the black ones, which are much rarer, show decreased mortality, and especially in western Canada, which is drier, they're observing increased mortality, which is consistent with an idea of increasing drought stress in boreal forests, and ultimately an initiating biome shift where the optimal conditions for boreal forest growth are moving north with climate change. Stepping back from that and thinking what that might mean for the 21st century, you cannot decouple it from the fact that the disturbance regime, and this shows fire events since the 70s in Canada and Alaska, are extremely important in regulating the carbon cycling of boreal forests as well as their species composition. There's mounting evidence that the fire regime is increasing. We see extreme fire years in the last decade with large fires that burn severely, and those are projected to follow along the trend of warming to increase into the 21st century. And it's the confluence of those two. We're seeing biome level changes that are consistent with widespread drought stress, which would continue into the 21st century, and at the same time, much more stochastic events that are disturbance related also on the rise. And it really raises the questions of whether regime shifts, tipping canoes, could really dominate or determine what the biome looks like in the coming century. So I'll pass it on to Andy from here.
Okay, so what I want to talk about in the next couple minutes is essentially our attempt to see if we can use tree ring data to see a regime shift coming. The thing about rapid ecological changes is that they're really easy to see in the rearview mirror. It's really easy to see them once they've already happened. It's a lot harder to anticipate their arrival. In this particular case, the regime shift in question, notably the potential loss of some area of coniferous evergreen boreal forest, is one that comes along with some significant changes in the ability of the landscape to provide ecosystem goods and services. It comes along with changes in the fire regime and in all kinds of things that people care about. So it might be nice to know ahead of time that we are headed down a road that could ultimately lead to our metaphorical canoe tipping over and getting us all wet. So what I'm going to try to do is show you some data that we think are providing hints that rapid change is possible in this part of the boreal forest. So a lot of attention that has been paid to the boreal forest over the last couple decades has focused really on the northern limit, on the place where the boreal forest meets the tundra right here. So here's boreal forest, mostly white spruce, and then you're starting to get little bits of tundra vegetation up here. And there's pretty good evidence at this point that the northern edge of the boreal forest is creeping its way gradually north. That northward creep of the boreal forest is in some ways an inherently gradual process, simply because it takes a long time to go from a seed to a tree that's big enough to actually influence characteristics of the landscape in some way that we care about. So this is a process that's ongoing, but what we started getting interested in was what's, at the same time that this northern limit is creeping its way north, what's happening to the southern or warm edge of the boreal forest. So Peter just showed you some data that speak to that a little bit. So some of those circles he was talking about are right here at that southern limit of the boreal forest. So in this map, these little triangles are actual closed boreal coniferous forest, and south of that, you can't, it's not shown on this map, but south of that is a widespread area of aspen parkland, and south of that you get into grassland. So the southern limit of the boreal forest corresponds to this point on the landscape where it starts to get particularly warm and dry. And there's some evidence from both tree ring studies and permanent plot data that there may be an increase in mortality of spruce at the southern limit. But what's really interesting is that that same transition from boreal coniferous vegetation to grassland happens in places all over the interior of Alaska. So along most of the major river drainages in interior Alaska, you find these very steep slopes like this, where compressed into one space that's maybe a couple tenths of a kilometer long, you get that continental transition. You go from evergreen spruce forest to aspen to grassland all in one fell swoop. And these little grasslands have actually been proposed as potentially relics of the mammoth steppe that Dan was talking about. So we're really interested in what's happening at this border of the boreal forest. And partly why it's so interesting is that death has the potential to be an inherently more threshold-driven, rapid process, right? Trees can die instantly. They can go from being alive to dead in a day. So you can lose a spruce forest pretty much overnight. Gaining a spruce forest is a little bit slower. So our hypothesis is that if there's going to be rapid changes in the boreal forest, this would be a good place to look for them. And so what we speculated going into this was that as it gets warmer and drier, based on what people know from studying the boreal forest down here, we hypothesized that aspen, which is more tolerant of warm, dry conditions, it grows much better in droughty conditions than spruce, that as it gets warmer and drier, spruce growth would become slower and slower, aspen growth might increase, and that we might see evidence of spruce forests potentially losing their competitive dominance over aspen. So what we're going to try to do is use tree rings to look for any evidence that rapid change may be lurking out there in the future at this boundary. So again, before I go to that, the slide that demonstrates that we were wrong, I'll repeat what we expected to see. What we expect to see is that spruce up here, which are growing on these steep south-facing river bluffs, right at the very limit of presumably of warm, dry conditions they can handle, that in years when spruce growth is unhappy, we would expect to see aspen growing relatively quickly. So this potential indication that aspen are doing better than spruce. So we went out and collected a bunch of tree ring data, and these are tree ring widths. So the y-axis is an index of tree growth, so bigger numbers are faster growth. And here's time. And these are two sites at which we have both spruce and aspen tree cores from the same general vicinity. And the first thing that we noticed was that, in fact, growth of these two species is more or less in lockstep with one another. They have exactly the same years of low growth, like here. They have the same years of high growth. At this site, they're deviating a little bit in the recent years, mostly because aspen is a very short-lived species, and these are pretty old aspen trees that are just reaching the end of their life, most likely. But by and large, the growth of these two species seems to be remarkably similar to one another, which was interesting and was not at all what we expected to see. So the next step in our analysis was trying to understand why. What is it that these trees are responding to? What are the conditions that are promoting rapid growth? What are the conditions that are promoting slow growth? And what can they tell us about the potential future of this boundary? So we used a statistical technique called regression tree analysis, which allows us to describe how the growth of trees, in this case, changes as a function of climate. And so we match up tree growth and climate, and we look for the relationship between those two things. And what we're able to do then is to define the conditions in which both aspen and spruce grow the best. And I'm sort of skipping over the intermediate stages in the analysis and showing you the cartoon of the take-home message, where the green bars in all of this shows you the range, in this case of May temperature, in which aspen growth or spruce growth is highest. And what you see is that for both species, the very highest growth occurs at this left margin of the graph. The gray bar for each site indicates the actual range of observed May temperatures from 1902 to 2010. And so you can see at this particular site, May temperatures can range from about 4 to about 12 degrees Celsius. The fastest aspen growth occurs when May temperatures are between 4 and 6 degrees Celsius. And that's consistent across the board at all of the sites we looked at, that the fastest tree growth is in the coolest years for both aspen and spruce. We don't see any evidence that aspen are somehow benefiting from warm years more than spruce. Both species grow best in the very, very coolest years. Note that these green bars are pegged to the very lower limit of May temperatures that are observed at these sites. Spruce growth is also best at most sites in wet years. So if you picked up a handout on the way in, there are two graphs on the handout. There's a graph that shows equivalent data for aspen, but that I pasted in the wrong graph, and so it actually doesn't have May precipitation on the x-axis, so you'll have to scratch that one out. It actually has winter precip on the x-axis. So you can either cross out May precip and write winter precip, or just cross it out entirely. But the basic pattern for the two species is the same, that when we look at how growth responds to precipitation, we see the very fastest growth, these green bars, in the very wettest years. So for example, if you look at, except at these two sites, which are doing something different, if you look at Calico, May precipitation can range from about 10 to about 40 millimeters. The fastest spruce growth is in those very, very wettest years. So tree growth is best in very extreme conditions, in extreme cool and extreme wet years, for both aspen and spruce, which we did not expect. We expected, again, that aspen would be more able to tolerate warmer and drier conditions. So the fact that spruce growth is optimized, that tree growth in general is optimized in the very extreme, coolest, wettest years, suggests that as it gets warmer and drier in the future in Alaska, that could be problematic for these species, because the conditions in which they experience optimal growth will occur presumably less and less frequently. The second clue that we had that rapid change may be possible is that when you look at the shape of the relationship between tree growth and temperature, so if you made a graph of tree growth, which would be the absent y-axis here, as a function of, say, May temperature, what you see at site after site after site, and I've turned it all into one cartoon here, but this pattern shows up over and over again at every single one of our spruce sites, that when May temperatures are low, growth is high, and it doesn't really change as May temperatures warm. It's sort of unresponsive to May temperature. May temperature hits a threshold of about 5.5 degrees Celsius, and growth starts to decline pretty steeply. So you see this period of steep decline in growth, and the precise location of it varies a little bit from site to site, but it's right around the sort of 5 to 6 degrees Celsius May temperature seems to be some critical point. Growth declines quickly as May warms past that point, and then growth is very low when May is warm. We see the same thing with winter temperatures. This is February to April temperature. And again, growth is high when February to April temperature is low. In years when February to April temperature crosses this threshold that's at about minus 10 degrees Celsius, growth declines pretty quickly. So these thresholds mean that there's the potential for very small amounts of climate change, small amounts of warming, to produce relatively large changes in tree growth. So you could imagine a scenario where if average May temperature in interior Alaska were sort of down in this range, then tree growth would mostly be high. And then if climate warms and most May temperatures are just a degree or two warmer, let's say average May temperature increased to 7 degrees, and I'm making these numbers up. That's a small change in climate, but it could produce a very large change in tree growth. So these threshold responses cue us that there might be the potential for rapid change. So the key findings are twofold. One is that both tree species seem to grow best in the coolest, wettest years. And the second is that for both tree species, there are thresholds in the way growth responds to temperature such that small amounts of warming lead to large reductions in growth. And together, these patterns suggest that rapid change is actually quite possible in these forests, that small amounts of warming could lead to large changes at this boundary. And what we would expect to see is not necessarily the replacement of spruce by aspen, which is what we expected to find, but it looks like you could see the wholesale loss of both species and potentially the expansion of this more droughty grass, sagebrush vegetation. That's a little speculative, but that's sort of where these would point. So at this point, I'm done, and I think we will open it up to questions.
Okay, do we have any questions?
Thanks, Peter. Is it on or off? On. Goody. How confident are you in assuming that this relationship will continue, because we don't have future temperature records? So I'm trying to understand, are you sure, half sure, not at all sure?
Yeah, that's a great question. By this relationship, you mean the relationship between tree growth and temperature?
Obviously, yes.
Yeah,
and not only temperature, but also wetness and dryness.
Right. That's a fantastic question. And I would put my sureness that relationship will continue in its current form at, I think, somewhere less than half sure is what I would say. I think I'm somewhat less than half sure for a particular reason. So the other thing we've been doing that I haven't showed you the data about because it's still too preliminary is trying to actually answer that question. What we've been trying to do is divide the 100 years of climate data we have into two sets. warm years and cool years, and look to see if the relationship between growth and temperature or precip differs between times when Alaska's warm and times when it's cold, and it appears that it does, in ways that I haven't quite understood yet. So what I know is that the way that trees respond to climate does seem to be quite variable, and we don't really understand why. But the implications are that as we move forward, especially into novel climate regimes that are quite unlike anything we've seen in recent times, trees might surprise us. They may start to respond in ways that are different than what we see. So I think we do have to be cautious about projecting too far forward from these results.
Just to follow up for a second, is there anything in the literature not related to Alaska that one could refer to? I don't mean that you have to read some citation, but I'm looking to see whether this may be a generalized Alaskan alone, or maybe it's a worldwide issue.
I think it's probably pretty worldwide. So Roseanne Dorigo at Columbia University she wrote a really nice paper in 2008 that summarizes a whole bunch of data on this phenomenon of tree growth response to climate changing. And then Andy Bunn, who just slipped out conveniently, has also done some work on the subject. And there's some work in Europe, and I'm forgetting the names of the authors, but they've found similar findings where the growth response is changing. So I suspect it's more widespread than Alaska. Everybody's still a little bit puzzled by it, but.
Yeah. Okay, thanks.
Do we have any other questions?
I'm Ned Roselle, Alaska Science Forum. Andrea, you said high temperatures in February through April also lead to growth declines. Why might that be? I don't picture the trees as growing then.
Yeah, they're not growing then. And so there are two possible hypotheses. One is that you could imagine a scenario, and this is largely coming from research on eastern U.S. tree lines. So I'm not sure how applicable this is to Alaska, but you could imagine a scenario where warm temperatures in winter for an evergreen species that still has its leaves could potentially, especially towards the latter end of that period, March, April, could actually warm leaves up enough that they could unfreeze and start to actually lose water at a time when the soil's frozen and they can't replenish that water. So there's a whole literature on winter drought stress that happens because of that mechanism. And so what you see is that in the following summer, growth will be reduced because of what essentially amounts to winter injury and winter drought stress. So that's one possibility. The other possibility is that warm winters are somehow, that there's something else about those years in which winter is warm that is actually what's stressing trees. So it could be that that relationship is actually masking some underlying phenomenon where if it's warm in winter, it also is dry in June or something. I'm pulling that out of thin air. And that actually what trees are responding to is the latter thing. And what we're seeing is a correlation driven by complicated climate analysis or complicated climate interaction. So we're trying to dig into that a little bit and see if there's something like that going on. Because yeah, they're not growing. So it's whatever it is that's happening in winter is somehow an effect that's being translated into their ability to grow in the summer.
Hi, Mason Inman with National Geographic News. And I'm just wondering if there are some places where there are already forests dying off, maybe just small patches, but where there seems to be some sign that this kind of process is already happening, because even though the average warming is, a degree in the world, then it's higher when you are up north, right? So yeah. I would think that there would be some places that had already been pushed through this threshold, and I don't know if the satellite data would be enough to be able to see this kind of thing, or if you'd have to be on the ground looking at small patches, but I'm just curious if there's any sign of this kind of thing happening already.
Do you want to?
I can answer on the satellite, but that's something that people are looking more and more into. There's efforts underway to get at tree mortality at global scales also, almost. The index that I illustrated here is probably not optimal to do that, because a dead tree is hard to recognize until it loses all its leaves, and there's a lag there in that signal. So from the satellite record, I'm not aware of high latitude examples.
And then from sort of on the ground observations, the places where people have identified really widespread mortality are, like Peter was showing, that paper that was really looking at the southern boreal forest. What gets complicated where we are is that there are other agents of mortality that may be interacting with warming. So, for example, there's been a spruce budworm outbreak in interior Alaska the last several years. And so you have trees that are being defoliated by an insect, and you could potentially have events like that causing mortality that may be underlain by underlying physiological stress driven by climate. So it's a hard question to answer, because there are trees dying in places in interior Alaska, but there's oftentimes at least another proximate cause. And we don't fully understand the ways in which climate change is going to interact with those things like insect pests that are causes of mortality. What I can tell you is that at the sites where we sampled, the trees still look perfectly healthy. So our hope is that these kinds of tree ring analyses can give us some insight into what may happen long before it does. Because we're not seeing, we're not measuring mortality, but when you walk through these forests, you don't see huge numbers of dead trees. So,
just really quickly, aren't the spread of bugs another example of a regime shift?
Exactly.
The spread of
bugs.
Of bugs, yes, exactly.
Yeah, so there's examples from Western Canada in particular where they act out at really large scales, and that is observed in satellite data. And it's exactly one of those mechanisms that play out at really large scales and have legacy effects.
Right. And you would actually, you'd really expect that insect pests could be a really important compounding trigger where, if you imagine a scenario where trees are becoming increasingly stressed by climate and their growth is slowing, and then you add in a novel insect pest who's either able to reproduce faster because it's warmer, or who has spread into an area it didn't used to live in because it's warmer, that interacting with somewhat stressed trees could produce vastly more rapid change than either thing happening independently. So that's really plausible, and there are people studying that right now, in fact.
Do we have any other questions?
Lizzie Grossman, freelance, and this is a question for Andrea. I'm curious, how is what you're observing in that southern edge of the boreal forest, how may that be related to what's being seen up in the tundra, where things have been shrubbing up and there's such an increase in vegetation due to either gradual or not so gradual shifts? And I was just wondering if there's any relationship in those events in any way.
That's a good question. So I suspect that the relationship between those two events is that both these really warm sites along river drainages in interior Alaska and the northern limit of tree line are both ecological boundaries that are very sensitive to temperature. They happen to be sensitive to temperature in different directions. That on the one hand, up north, rising temperatures are allowing shrub species, and in some cases trees, to grow in places that were previously too cold. So you're seeing this increase in vegetation. Here in interior Alaska, in these very warm sites, a rise in temperature has the opposite effect, where you're pushing temperature past a threshold, where potentially you could see an expansion of this herbaceous vegetation. It becomes a really interesting, I think the interesting exercise to go through would be to start thinking about a vegetation map of Alaska and think about the landscape and think about, from the perspective of the way that vegetation influences climate, for example, what are the interacting effects of, on the one hand, spruce expanding to the north, which is going to make the surface of the earth darker, lower the albedo, potentially magnify warming. And then if at this boundary we started to see an expansion of grassland vegetation, which is brighter and has a higher albedo, thinking about the interaction between those feedbacks is a really interesting question, I think.
Hi, Stephanie, livescience.com. I'm wondering if you can expand a little bit on if these possible rapid changes were to occur, what that might look like, what time scale, what might go on with wildlife, and that sort of thing.
That's a good question. Any of you guys want to take a swing at that?
Go for it, Peter.
When I think of it, following up on what you said, we're seeing the ideal envelope of boreal forest growth move north, and ecosystems don't follow the climate one-on-one because tree establishment is limited. Shrubs can react more quickly probably in terms of establishment than trees, etc. What we observe is consistent with projections for the second half of the 21st century. In terms of what that northward shift of boreal forest would look like in the starting stages. I don't have an answer for when tipping canoes and widespread shifts between regimes, at what time scale they would play out. But I think we're at a stage now where the question is whether they could play out in that time frame of the 21st century. Because if you look at the range of temperature increase, we're very close to moving between regimes what we see in situ, or potentially moving between regimes.
And I would just add to that I think that, so we know that at the northern limit of boreal forest, that's already happening. There's already, that started decades ago, boreal forest moving north. I think at the southern, at these warmer edges, in interior Alaska, and presumably this may also be true down in Alberta, for example, but in interior Alaska, I think what we're starting to have is enough pieces of evidence to suggest that rapid change is possible. I don't think we know enough yet to even begin to put time limits on it, because there's so many complicated interactions. The insect pest question is a great one, and we just don't know enough yet about how that's going to play out. So I think identifying a time frame in which it might play out, we're not there yet. Where we are is at the place of being able to say with some amount of confidence that, yes, this is a place where rapid changes that you might call a regime shift seem plausible.
So you think over the next century or over the next 50 years that it's likely?
What do you mean by likely?
Okay.
Do we have any other questions from the floor or from the chat? No further questions? Okay, that's it then. Thank you very much for your presentations. Thank you all for coming. Our next and final press conference for the meeting will be at 11 o'clock. It's Changing the Energy Landscape, More Efficient Wind Farms and Cleaner Biofuels.